All right, welcome everyone. So in this part of the lecture, we are going to be talking about how to prove that the given problem is NP complete. This is a common question that's often asked in exams. You're given a new problem that you've never seen before, and you're asked to prove that the given problem is NP complete. So before we dive into it, let's just do a quick summary. What are the classes P and NP? Essentially, these are complexity classes. A complexity class is a set of problems that can be solved within certain usage of a given resource, such as time, space, could be something else, but mostly time and space are the two common resources. In fact, here we're talking about the time as the resource here. So what's a class P? The class P is a set of languages or the set of problems that can be solved by a deterministic Turing machine. And the class NP is the set of languages that can be accepted by a non-deterministic Turing machine, also in polynomial time. So I did not say that for P, but both of them are for the set of problems or the languages that can be accepted by a deterministic or a non-deterministic Turing machine in polynomial time. And again, when we say polynomial time, we mean with respect to the size of the input. So if you're given a string of length n, then you have n power c steps to accept it. It takes that long. That's what the class P and the corresponding class NP stands for. These are the sets of languages, also the sets of problems. If you are confused about why we call a set of language a set of problems, there's a separate video for that, so you can kind of watch that one as well. And the class NP complete is the set of problems that are in NP and that are also NP hard. That means other problems in NP can be reduced to those problems. So that's the class NP complete, okay? And when we use the word reduced, we mean the following. We say when we're given a problem B, and if we have a hypothetical solution for problem B, that can be composed by doing a reduction from B to A, and then by using the algorithm, by using the solver for algorithm A. When we are able to do that, we say that the problem B reduces to problem A. We also use the term transform. And then we make the observation that problem A, in that case, is the central problem. And therefore, we make the conclusion that problem A is at least as hard as problem B. So when we look at this diagram and we see that the problem B is outside and that the input for the problem B, which in this case is X, is being reduced from B to A, we may think that problem B is larger here, but considering that the reduction itself does not take a disproportionate amount of time, the main conclusion to draw here is that the problem A is the central problem, and it is at least as hard as problem B. So that's the concept of reduction. It can also be, another term can be used as adjustment as well, or transformation as well. And sometimes transformation is perhaps even preferable in my opinion. But the common term used inside the theoretical computer science is that of reduction. And here's a little example. Let's suppose we have a sorter that can only sort inputs that are given as long as the length of the input is in powers of 2. Now, if we have to use the sorter to sort, let's say that has 1,000 elements, but our sorter can only solve 1,024, that's fine. We can play a little game here by adding some 24 extra elements to be that are either negative infinity or positive infinity, use the sorter, and then remove them at the end. These are kind of transformation or adapter that we would often build. And that's the concept of reduction here. Another background material that we must cover before we talk about how to prove the NP completeness of a new problem is that we must know about this problem called SAT, the satisfiability problem. Again, if you want to deeper dive into that, watch a separate video on the satisfiability. But the satisfiability problem in a nutshell is that you're given a Boolean formula. It could look something like this, x1 or x2 or x3. And so it has a bunch of these conjunctive clauses. So there are all these and statements. Inside the and statement, you have or statements. So as long as something from here is true, and something from here is true, and something from here is true, you will be able to make the overall formula true, which means that the formula is satisfiable. Now, each of those inputs do have relation with the other. For example, here, if you have x1 and here you have nx1, if you do set x1 to be true, then nx1 will become false. And then you have to figure out a way to make this clause true by setting something else to be true, which could then have a complication on something else. That's the reason this is a interesting problem, and that's called a satisfiability problem, that given the formula, figure out a truth assignment. Truth assignment means true or false for all of the xi literals, xi variables, x1 through however many you have, such that the entire formula becomes true. That's the satisfiability problem. Stated in a question way is that, is this given formula satisfiable? That means that is there a truth assignment that sets it to be, that makes the formula to be true. And what is the relevance of the satisfiability problem in this case? Is that satisfiability problem, by the virtue of Cook's theorem, is actually the original NP-complete problem. And what does the Cook's theorem say? Cook's theorem says, in a nutshell, it says that any problem in NP can be reduced to satisfiability problem. That means that if you can solve the satisfiability problem, you can solve any problem in NP. That is what, in essence, makes satisfiability problem to be a central problem, or the NP complete problem. It is in NP, and it can solve any other problem in NP. Therefore, we refer to SAT as the original NP complete problem. And that's essentially the result of very remarkable result by Stephen Cook. So often referred to as Cook's theorem, also commonly referred to as Cook-Levine theorem as well. Okay, so that's the background on satisfiability. Now let's understand our NP completeness proof method. Our NP completeness proof method essentially does the following. It says that, let's suppose you have a new problem. The problem X is NP complete. And if you want to show that the problem X is NP, well, first of all, you show that the problem X is in NP. So that means that there is a polynomial time verifier exists for X. Essentially, that means that you're given the problem X, some instance, and you're given the solution for that. You can easily check if the solution is correct or not. You should be able to show the verifier for that. As an example, if somebody gives you a Sudoku solution, you can check in polynomial time that yes, the solution is correct or the solution is not correct by doing a distinctness check on each row, each column, each mini square. So to verify a given solution is not hard, and that's why we say that the problem X, the Sudoku problem, is in NP, and similarly you have to show that this problem X is in NP. That's generally the easy part. So you show that the problem X is in NP. Then we come to the harder part, which is the reduction part, that we pick a suitable known NP complete problem, for example, satisfiability problem that we just talked about, and we show a polynomial time algorithm to transform S into an instance of X. And for that, we recommend this mnemonic. Just to make sure that you remember the exact steps here, the mnemonic is SOX ReStox. And SOX ReStox essentially stands for that put SAT outside the box and reduce SAT to X. And what box we are referring to, again, I'll show you the reduction diagram, but that's the mnemonic that can help you to kind of prove any given problem X to be NP complete. And again, to prove X to be NP complete, you will first of all show that it's an NP by using a simple verifier. Then you want to show that the problem X is also NP hard. And that's what this diagram will kind of look like. So again, the important part here is that you remember that you have to put satisfiability problem outside the box. X inside the box, inside this big box, and you have to reduce SAT to X, which is then written mathematically as SAT using this less than equal to P symbol with the P subscript X, which means that there's a polynomial time reduction from SAT to X. In other words, if you solve X, you can solve SAT. That's typically what you want to show. And if you want to look a little bit deeper into the transformation, you're given an input for problem SAT, which means it's a Boolean formula. You transform that to the X input. That means we will call that to be the lowercase x, which you then give to the algorithm for X. And once that gives you a true false answer, you have your true false answer for the satisfiability problem. So that's what the general SOX ReStox mnemonic helps to make sure that you prove in the correct direction. If, for example, by mistake you put X outside and SAT inside, that particular result has no specific value. That has no specific value because in that case, you're not able to show that what's the end result. That's essentially what the Cook's theorem already showed, that every problem can be reduced to SAT. Now what we're doing is we're using the transitivity to say that every problem in NP can be reduced to SAT. SAT can be reduced to problem X. Therefore, transitively, every problem in NP can be reduced to this problem X. And that's why it's important that we show in this direction. That's, again, the SOX ReStox mnemonic. As a very quick example, and we won't go into the details here, but if you just want to show that the click problem is NP complete, we will use the same exact method. First of all, we will show that the click problem is in NP. That means we can validate a given solution. And then we will show that the click is hard by transforming the SAT problem to the click problem. And again, you can kind of cover that in a separate video on how to do that transformation. But this is what essentially this methodology shows here. Now, I do want to make a clarification that when we use SOX ReStox mnemonic, in that mnemonic, S really stands for a suitable NP complete problem, not necessarily SAT problem. Okay. So that means that we can actually start with any known NP complete problem, because if the problem is known to be NP complete, that means all problems in NP can be reduced to that. And if that problem can be reduced to your problem X, then effectively you have used the same exact methodology to also prove that X is NP complete. And in this diagram here, we are, instead of using SAT, we're using the Hamiltonian path problem as our starting problem and doing the reduction from the Hamiltonian path to the problem X. This is perfectly acceptable as well. And in fact, you should try to use whatever you think is going to give you the easiest reduction, whatever you think is the closest problem to this given problem X. That's a quick summary that to prove that a given problem X is NP complete, do two things. First of all, show that you can verify a given solution. Not find it, but verify it, okay? And usually those kind of things are easy. Your polynomial time algorithm should be 3, 4, 5 lines at most, saying that, okay, if given a solution, I will check that it matches up. You're simply checking, okay? Then you want to prove that the problem is NP hard by using this SOX ReStox framework, but just choose a well-known acceptable NP complete problem. Could be SAT, could be Hamiltonian path, could be something else. And usually in the question, there might be some clue to saying, hey, you can use any of those 5 or 6 or 7 known NP complete problems. So feel free to use any of them. In practice, when we see new papers talking about a new problem, showing that new problem to be NP complete, often they will use a variety of known NP complete problems as their starting problem. And those are all perfectly good proofs. So that's all I have for you today. Just go through this a few more times to make sure that you understand the framework and you prove the result in the right direction. Because if you prove it in the wrong direction, you're kind of just showing a small variation of this of the Cook's theorem, which is not what we want to do. Rather, we want to show the reduction from a known NP-complete problem to the new problem that you want to show is NP-complete. So that's all I have for you today. Have fun, keep learning, okay?